First, I'd like to thank the organizers for inviting me to give this talk. Today, I'm going to be talking about an area that I think is particularly important given the rise in machine learning techniques, where we focus on the practical machine and deep learning techniques used in scanning probe microscopy. In a variety of different characterization techniques of materials, there's been a growing trend to increase the dimensionality of the data acquired. One of these in scanning probe spectroscopies is called band excitation piezo response force microscopy. In this technique, you apply a bipolar triangular waveform, shown here, which switches a material through its ferroelectric transition. Then, by applying a band excitation waveform throughout this process, you measure the full cantilever resonance, which gives you spatial maps of the piezo response, contact resonance frequency, the amplitude of the response, the phase, etc. The challenge is that band excitation is very difficult to analyze. So you have these 4-channel hyperspectral images where there's a lot of information and you're trying to extract some of the detailed characteristics of the response that you're interested in. Even if you were just to look at the piezoelectric hysteresis loops, you notice that there's a lot of subtle details within the hysteresis loops that are important to capture, but that are very difficult to extract using conventional analytic approaches. So to address this, there's been a lot of work in applying various forms of machine learning to try to extract information from these large data sets. And this has been made very, very easy by a collection of open source packages, including PyTorch, scikit-learn, TensorFlow, Keras, which make it really quick and easy to deploy these machine learning approaches with very minimal experience. The problem is that it's really unfortunate that machine learning tends to work so well. It's actually quite hard to train a bad machine learning model, particularly when you start to talk about large models that can be over-parameterized. Even small models, it's relatively easy to get accuracies that appear good, for instance, within 10%, that maybe are not encoding the physics in the most appropriate way. It is also very easy to deploy machine learning without a clear understanding of the mathematics of the model, and this allows for the machine learning to sometimes provide results that seem to be good, but actually are not encoding the important physics. This kind of poses the question of if you were trying to synthesize a material, would you want to be able to make it without understanding how it was made? And the answer, I would feel, is probably not. So generally, when we think about what we want machine learning to do, there are a few things. We want machine learning to be fast. So we want it to accelerate how we turn data into actionable information that we can use as physicists to guide our understanding. We want machine learning to be better. So we want it to build simplistic and highly performant models that explain physical phenomena in parsimonious ways. We want the machine learning to be less biased. That means we want the constraints that we apply to be only based on strong physical priors or that are statistical in nature so that they don't conceal or distort the physics included in the model. Recently, there was a paper, Better, Faster, and Less Biased Machine Learning, that claims that they achieved all of these for the exact case of electromechanical switching and ferroelectric thin films. But the problem with machine learning is it's so easy for machine learning to trick the user to assume that they get really good results, even when they don't. So let's look a little bit more about how you practically apply machine learning and how you can evaluate if your machine learning model is actually doing something that you want it to do. So one of the key tools that machine learning practitioners have is they have benchmark data sets. And this is why I chose to start to analyze this, because this work was analyzed 2 different ways. So there was this original paper published by myself and colleagues where we used a neural network-based approach to analyze this data. And then this data was used again in the second paper using a simpler technique, which was proposed to have better, faster, and less bias applied. But what's really nice about using having a benchmark data set is it allows you to validate the performance of your model and compare and contrast. So let's talk about this first technique that claims to be better, faster, and less biased. In this approach, they used a technique called dictionary learning. The process starts with first applying a denoising filter. Then they subtract the mean from each spectra, because dictionary learning struggles with large changes or variances in the mean. They normalize the data using a multiplication factor, which they chose. And then they conduct dimensionality stacking, where you stack 2 dimensions, the piezo response and the resonance, one on top of each other. And they fit their model using dictionary learning based on scikit-learn. This was preconditioned by using the k-means clustering results. And then they conducted analysis and interpretation. So if we look at the mathematics of what dictionary learning is doing, it's relatively simple. What it's doing is it's trying to minimize this function, where this function tries to compute some atoms or some dictionary D, which when multiplied by alpha results in a small loss. To try to make the data more interpretable, It's common to add a sparsity constraint controlled by a hyperparameter lambda, which tries to minimize the value of alpha so that it doesn't go too large. To avoid explosion of this dictionary value to compensate for alpha, you then have to add a L2 norm constraint to be less than 1 so that the sparsity effect actually comes into play. If we analyze what, from a mathematical standpoint, this function is actually doing, its descriptive power comes from a linear combination of d and alpha, and then the sparsity is enforced by the lambda parameter. The key bias that is implied in this method is that k must be predetermined. So we must need to know ahead of time how many different dictionaries we want to learn. So now let's look at the second approach, which relies on deep recurrent neural networks. So we started by applying a denoising filter to the data. We normalized using a standard scalar, trained the model using a deep neural network, and then conducted analysis and interpretation. So that in this process, there are clearly less steps because the neural network is able to learn and accommodate for the complexities handled within the data. So now let's look at the mathematics of the deep autoencoder. So this neural network starts off as an autoencoder structure. So it has both an encoder and a decoder, which is the encoder has learned to use a statistical representation of the data. And then it's compressed in this low dimensional layer called the embedding layer. And then it's decoded using the decoder. And each of these individual dots represent neurons. And all a neuron is it takes an input, multiplies it by a weight, adds a bias, and then passes it through a nonlinear activation function. And by imposing this nonlinearity, you can accommodate nonlinear responses in your model. In addition, each of these neurons, to include the concept of time, was a long short-term memory neuron. These are taken from natural language processing. And what they do is, because we're dealing with spectra, they allow us to consider the data recurrently or through time, which is not included in the dictionary learning model. Finally, we want to add some sort of constraint on this low dimensional layer. And in particular, in this case, what we did is we used a KL divergency constraint. So what this math essentially means, if you boil it down, is we have the second term, which is a KL divergency term, which essentially evaluates the difference between the output of this low dimensional latent space and some prior distribution, in this case a Gaussian, and then multiplies it by a beta term, which sets its magnitude. By tuning or optimizing this beta term, you're actually disentangling features, because as beta becomes large, you're forcing the latent space to become more and more Gaussian. One useful approach to try to build and understand the efficacy of a machine learning method is to build a toy data set with a known ground truth. So here we designed a bunch of different nonlinear functions, and we built spectra, just like what we had, out of linear combinations of these nonlinear functions. So we started off by generating 500,000 random spectra based on these nonlinear functions and trained each model. And if you look at the results from the dictionary learning model and the deep autoencoder with a number of components set equal to 3, which is the number that we know we have from our toy data set, you can see that the deep autoencoder is almost an order of magnitude better in terms of its mean squared error. This does not mean that the deep autoencoder is better. It just might mean that it's overfitting the data. And also we have to consider that the deep autoencoder takes significantly longer to train than the dictionary learning model. However, there's a practical challenge with applying a method like dictionary learning, which is we don't know most of the time what the number of components is that we wish to extract. So if we were to set the dictionary learning components to 8 or 10 or 12, the mean squared error drops precipitously. So we need to do a much more detailed evaluation of these machine learning methods. Since we were just comparing 3 nonlinear functions that were linear combinations of one another, we can take an RGB image, for instance, this is an image of my dog Nala, and we can use this to generate more spectra and see how the latent space looks when we use these different methods. We compute the dictionary learning on 3 components. Again, we can see that Nala's features are clearly detected. But if we go and we look at what the atoms or the end members look like of the spectra, they just look like smoothed out or averaged out versions of the original spectra. We can look at this a step further. If we slowly increase the value of alpha, we can generate what the spectra looks like. And with the dictionary learning, what you see is that the curves are essentially devoid of any of the important curves and features that were in the original spectra. This is because the mean squared error in the dictionary learning doesn't care about the subtle features of the spectra. It only cares about having close to the mean squared error or the average response. So if we then were to try to interpret these spectra, they wouldn't be that informative in terms of guiding our physics. Now let's compare what happens with the deep autoencoder. So in the case of an autoencoder, we don't know ahead of time how many different latent parameters to choose, so how many different neurons to have in the embedding layer. So what we do is we can schedule this beta parameter, which acts as the disentanglement parameter, and we can watch what happens as this starts to train. So we can see here at beta equal to 0.1, so we can start to see some of the features of Nala, my dog, coming out. But as this beta value increases, what you're noticing is more and more become just noise that is representing the Gaussian. And this is disentangling the most important information from, the spectra. So we can keep scheduling and increasing this beta value until we achieve a desired number of components, which we think are important or physically meaningful in the spectrum. So in this case, as we increase beta at around 0.13, which will be coming up shortly, you see that we condense down to having 3 important characteristics, which again show the key features of Nala in the image. If we then go on to the generator, we can see that the generator shows much more of the key characteristic features of the spectra. In particular, our spectra, the nonlinear transformation was a phase shift. And as you can see, particularly in the right-hand image right now, you can see that you're clearly seeing the phase shift in the spectra as we move or generate across these parameters in this latent space. So what this is showing is that the deep autoencoder is able to learn much more of the inherent shape and structure of the function. So we can compare these results one on top of another, and you can see that for our generated spectra, even though the spectra is not perfect, particularly there are a lot of cases where you can see these shifts between the green, which is the neural network prediction, and the red, which is the dictionary learning prediction. What you see is that in all cases, at least, the shape of the curve from the neural network matches much better to the actual raw spectra. And this is because the neural network cares about the time and the sequence and the pattern, rather than in the dictionary learning where it's just trying to minimize the mean squared error. Now that we've demonstrated that a neural network can at least capture the physical structure of a toy spectra much better than dictionary learning, it's important to validate if it actually makes sense on a benchmark data of electromechanical switching. So we took that benchmark data set, applied, and we again applied the dictionary learning technique and looked at the N members. So if we look at the N members, what we can see just out of the initial pass is that the first 2 N members look like classical ferroelectric switching with resonance behavior that looks like softening and hardening. This second feature shows a little bit of concavity in the piezoelectric hysteresis loop and a hardening step during ferroelectric switching, which is associated with a 2-step, 3-state ferroelastic switching process from C to A to C. If we look at the other atoms, however, we don't see any clear physics behavior that we can commonly interpret. Moreover, because the mean was extracted from this data before the dictionary learning was fit, the absolute position of these spectra are hard to relate back to the physics, even though they have physical meaning. So we can again use the dictionary learning as a generator and look how the individual spectra change as we change the alpha parameter. And as you can see, the first 2 parameters, they kind of stay as they are, with the second parameter showing some increase in this magnitude of this 2-step, 3-state ferroelastic switching process. But the other parameters really don't change, and it's very hard to understand what's going on in the different parameters outside of the first 2. If we now look at the deep learning generator, we can see that much more of the important structural features are identified. So here we can start off with this, in this blue region, we see the 2-step switching process. We can see in this image, as we increase the value, as we go towards this brighter region, what we're going to see is that classical softening and hardening process, and it's also going to increase in magnitude up. And here we can see that on the right-hand side, we have this strong positive value, which is associated with a strong negative concavity. So what this shows is that the deep learning model is able to much better represent the key small structural features in the spectra that are important physically to analyze and understand. So again, we can compare the results by looking at the reconstructions of the neural network shown in green, the dictionary learning model shown in red, and the raw data. And what you can clearly see is that the neural network is able to much better predict or reconstruct the fine features which are of physical meaning in these piezoelectric hysteresis loops. So for instance, this negative concavity here is clearly identified by the neural network, but it's completely ignored by the dictionary learning model. This too comes across in the resonance data, where the resonance tends to be missed. The peaks are less clearly identified by the dictionary learning model shown in red than in the neural network-based model. And this is on top of the fact that the dictionary learning model takes the mean of each spectra and removes that from the data so that it's actually a less challenging mathematical problem to recreate the reconstruction. So what ends up happening with the dictionary learning is it essentially just learns the general shape and average, missing out on the important key details in the spectra that are actually physically important. So to conclude, what we want is we want really fast machine learning models, and it's always best to choose the simplest model, but it can't be too simple, and this model cannot be a black box. We have to understand the mathematics. So you should always try to use the most simple model. So linear models like dictionary learning and principal component analysis are great first steps, but they need to be thoroughly validated and vetted before they're used to extract physics. If we really care about making our model much faster, we can think as a community about how we can go leverage hardware acceleration on neural processing units, for instance, FPGAs, to accelerate machine learning models such that they can be conducted with millisecond latencies. We want our machine learning models to be better. They must be performant, but to be performant, they have to be sufficiently validated. Every time you train a machine learning model, it is essential that you try to trick it and try to prove that it doesn't work in every single way possible. And it's particularly important if you're going to use it downstream to make physical interpretations. If you try to derive conclusions from overfit or underfit models, it'll only lead to false conclusions. We want our models to be less biased. This means only applying physics-based priors where there's known ground truth, or globally invertible transformations, for instance, standard scalars, should be applied to data. If you want to apply other constraints to your data, which is useful to make things more interpretable, it's very important that these constraints are soft statistical constraints that can be scheduled with hyperparameters and thoroughly investigated after the fact. I thank you for your attention, and I would like to acknowledge the students who actually do most of the hard work behind the scenes. I would also like to refer you to my website, m3-learning.com, which has a lot of our code that we always make openly available, as well as our data sets that we use for all of these studies. I look forward to getting questions in the live session. Thank you.